Hello, everyone. Welcome. In this video, we will give a guide and tips for chapter 23 of my Java book. Chapter 23 introduces a variety of sorting algorithms. We already had one sorting algorithms in chapter 7, that's the selection sort. And now we're going to look at other popular sorting algorithms: insertion sort, bubble sort, merge sort, quick sort, heap sort, and external sort. So let's first look at insertion sort. Insertion sort is to insert the element to a sorted sublist, the sublist as at the beginning. So this is the sublist. So let's have 15 numbers here. So now you're going to insert 65 into the sublist, has this one element. So this two now are sorted sublist, and then you add more. So this is continue the process until you get to the last one. And so everything is sorted. So this is insertion sort. The time complexity is order of n squared. So the next is a bubble sort. Bubble sort, you have all these elements. Now you compare the neighboring two elements if they're not in order and swap the two. So you continue and for this to the end. So that's one pass at the end. So the last one is the largest element. And then you continue another fast, do the same thing. So this is the maximum you have n-1 faces. So each time when you compare things, so this is the n times. So total is order of n square time for bubble sort. Merge sort works this way. So you have this elements in the list, you divide it into two parts and further split it into two parts until you cannot further split it. And now you do a merge. So this 2, 9 merge becoming 2, 9, 5, 4 become 4, 5. And this together it's 4, 5, 2, 4, 5, 9. And then you merge this two together. So this is the process, it's called a merge sort. Merge sort is quite interesting. It takes out of n log n time in the worst case. So it's pretty good. This is more efficient than other sorting algorithm we have used. So the next one is a quick sort. A quick sort is that you use an element from the list as a pivot to partition the list into two parts. So all the elements in list 1 is less than or equal to the pivot, and all the elements in list 2 are greater than the pivot. So the pivot partition the list into two parts. So the nice thing with this is you're not creating a new memory space for the list. So this is the in-place partitioning. So then you do it recursively and use the quick sort on list 1 and list 2. So this quick sort, the nice thing is the average time complexity, it's order of n log n. We can prove it mathematically. And the next thing is this heap sort. We have a data structure for this heap sort within a binary tree. So here it's a complete binary tree. So the tree, it's every level is filled except the last one. In the last one, and all the elements are placed leftmost. So, and another condition is that for each the node, you have the element, it is greater than or equal to its children. So here, and look at this first A and B, this both are complete binary tree, but this one here, 39 is less than 42, so it's not, the order is not right. So it's not a heap. This one is a heap. It's everything. This is a complete binary tree. It's right in order. So for this heap, we use this it's to insert element into the heap. It takes the time, it's out of log-in time. The log-in, out of log-in, it's the height of the tree, it's out of log-in. And remove element, it's also out of the log-in time. So using this is a heap. It's the we create a class for the heap right here. Is the heap class. So you can add elements to the heap and remove the root from the heap. So that also takes out of log-in time. So if you have n elements, you add each, it's the time it's out of log-in time. So the total is out of n log-n. And remove everything, it's also out of n log-n time. And so that after you remove it, when you remove it in the order, always remove the root. So this has become, this is the sorted elements. So that's the heap sort. It's a very neat data structure. The time complexity is out of n log n. So finally, we look at the external sort. And so there's before external sort, we also have this bucket sort. So the sort for the all the elements we have, we compare this. So you can prove that the optimum time, the minimum time you have to spend, it must be out of n log n time to, in the worst case, to sort everything. So you cannot do any better than out of n log n time. But if you don't have to compare things, there's a nice way is the radix sort and bucket sort. You don't have to use compare the elements. You use a special way. So this you can look at it, a bucket and radix sort, and they are more efficient for the if you sort integers. So you don't have to compare them and use the buckets. And so this to achieve very good efficiency. It's almost like linear time. It's out of n time. So the radix, there's a radix there too. So this is the very efficient time. So the number of digits. So let's say if you have integers and all the integers have 5 digits, the maximum 5 digits. So it's going to spend 5 times n. That's the time. So that becomes out of n time. All right, finally, the external sort. The external sort, if you have a very large data, you cannot bring all the data to the memory at the same time. So that's what we need to do, is to do it using the approach called external. So you bring part of the data and to the memory, sort it and put it back, and then it's using an organized way and to get everything sorted and put it back to the disk. So that is the external sort. Well, that is all for this chapter on sorting. So this is chapter 23 on sorting. So the purpose of this chapter too, the first thing is you're exposed to a variety of sorting algorithms, and sorting algorithms are very useful. The second is the creative approaches to sort. You can learn from these approaches and apply to other problems you will encounter. Thank you very much for watching. Goodbye.